Okay, welcome to part 4 of these lectures on physical metallurgy of zirconium alloys. In this part, I'll be talking about mechanical properties of irradiated material, strain localization, fracture toughness, and delayed hydride cracking. The focus being on irradiated material in each case. So let's start with mechanical properties in general. I would have said earlier in the first presentation, first part of this series, that radiation creates damage, displaced atoms. These atoms cluster together and form dislocation loops. And I think I showed you some examples of what they would look like, platelets. And the loops are basically dislocations in the matrix and harden it against deformation. So what you see for many zirconium alloys as a function of neutron fluence or dose or deep displacements per atom, if however which way you want to look at that, the hardness, or in this case hardness, increases very rapidly at the beginning of the radiation and then reaches a more or less steady state saturated value at very low doses, which is around about 0.03 dPa in many cases. In terms of fast fluence, it's about 2 to 4 times 10 to the 24 neutrons per meter squared. Here's some other data where we're talking about actual tensile test data, which is the yield strength and the ultimate tensile strength of zircaloy 2 after it's been irradiated in a BWR. And same deal, at a very low dose, we get a very rapid increase in the strength of the material, primarily from radiation damage, dislocation loop formation. And concomitant with that, we have this decrease in the ductility of the material. So with the strength comes a reduction in ductility or fracture toughness, if you like. Likewise, for PWR, some French work showing very similar results with tensile specimens. And the other thing, what this shows kind of nicely, is that if we're plotting the yield strength and the tensile strength together, the yield strength is naturally, in an unirradiated case, I can't go back. In the yield strength in an unirradiated case is lower than the UTS, but when you get to irradiation, because of the reduction in ductility, the yield strength and the UTS combine, tend to come together. Now, for completeness, I've also got some data here for ZIRC 2.5 niobium pressure tubes. The previous two examples were for zircaloys. So what we have here for ZIRC niobium pressure tube is the same deal. We have this very rapid increase in low doses. But what this also shows is illustrates one of the methods I've been involved in since I started work at Chalk River back in the mid-80s. It was very clear that you couldn't do a lot with TEM, but X-ray diffraction was a good tool for monitoring the microstructure evolution in a quantitative way. So the line broadening, or the integral breadth of the prism planes in the hexagonal lattice gives you information about the A-type loop density. So I mentioned in the early lectures that there are basically different planes on which you can get slip in zirconium alloys, but there's also different planes on which the loops form. And in some cases, you get loops forming on both the prism planes and the basal planes. Sometimes you only get the prism planes. But in terms of the evolution, the one feature of the microstructure that evolves very rapidly and you see the effect of very quickly is the A-type loops, the prism plane evolution, and that's shown here, and that's consistent with the changes in the UTS. As you'll see later, this gradual slope here over a long dose may reflect some gradual increase in the in the A-type dislocation loop density with increasing dose. That is, it's always approaching some saturated value over here. I should put this with some saturated value at high dose, but it also just simply, and I believe that we have evidence to show this, it reflects the C component loop evolution. So when I talk about C component loops, it could be a C plus A or a 6-2 of R23 dislocation loop. So, and in those cases, although the main distinguishing feature of the dislocations is it has a C component in the Burgers vector, it also has an A component. And the C component loops, as we'll see later, evolve over a much longer period. So it's fair to say that this early rapid increase and turnaround at very low doses is primarily from the A-type loops. This longer duration transition to something else may have something to do with the A loops, but in all likelihood is more to do with the C component dislocation structure, whether it be loops or dislocations themselves. Here's some tensile data to go with that, showing the drop in ductility as well as the increase in the UTS. So just like with the zircaloys, with the hardening comes a reduction in the ductility. And for this set of data, also we have the integral breadth, as I'm repeating that here now. Oh, I don't know what happened here. I don't know why that should have been there. Anyway, as I mentioned, we have this situation when you look at the evolution of the microstructure, because we have to associate that with the mechanical properties in Zucknagel pressure tubes. I'll start off by saying that initially we have, if we think about the TEM, what we will see in an electron microscope, this is the structure in the unirradiated state here. It's very messy, it's very high dislocation density, the fault's very bent, small grain structure, very difficult to get good diffraction conditions. And then when you irradiate it, it's just worse. It's just even more dense. You can see the loops here are lined up, but it's not nice. And likewise with the C component structure, a little bit easier to see because you got this when you're imaging with a basal plane reflection. A lot of this other stuff that you see up here is not in contrast. So we just see the C component dislocations and we see the effective radiation, and the primary response here is helical climb. So if we look at the line broadening and just want to pick up the A-type loops or defects which give a strain in the prism planes, we see this rapid increase and then a gradual change afterwards. Now, the rapid increase is because of that. The gradual change afterwards may be because this part also contains an A-type, an A component in the microstructure. So if we're looking at the C component, as you can see here with the dislocations, we can see that we're increasing the density of the C component dislocations, and we can follow that with the line broadening as we see here. And the point to note is that it occurs over a much longer period, whereas the A-type loop damager evolves very quickly and saturates at a very low dose. The C component structure evolves over a much longer dose range. This is going to be important later on. some of the early studies way back when people were starting to look at radiation damage, one of the obvious things to think about when it comes to loop nucleation densities is the effect of the flux. Now, focus here is primarily on reactor conditions and reactor data. But we do have some ranges of fluxes to deal with. If we think about some of the test reactor information that's available, we have one range of fluxes. This is for in the Cirrus. This is some data ranging from, in this case, 10 to 18 times 10 to the 17 neutrons per meter squared, which would be 10 to the 13 neutrons per centimeter squared. And when you compare that with CANDU reactor operating conditions, we have a much lower range of fluxes, basically an order of magnitude lower on average. And what we see when we plot the CANDU data against the Cirrus data, the Cirrus data is the Irradiated in blue here, there's not really much difference, and that would indicate that even though we have a factor of 10 increase in the flux, the neutron flux here, it has very little effect on the evolution. You should note that the Irradiated test data here is kind of tight. There's very little scatter in there, and that's because we have a series of specimens which are all taken from the same tube. So when you're manufacturing tubes, you have a whole range of variability that can exist from tube to tube. But if you take all your samples from one tube, there may still be some spatial variability in the microstructure, but the effect of the radiation shows up more prominently, as it does here for the blue points. When we're sampling randomly from many different tubes from very different locations along the tube, what you have is a bigger scatter in the data. So this is hardly surprising. Okay, so one of the features of damage in zirconium, which is dominated by these A-type loops, is strain localization. So one typical feature of damage in zirconium, which is also very similar to what's observed in stainless steel, is the formation of channels. So when you have an irradiated material and you test it, what is generally observed is a load drop at a certain point. So you'll strain the material elastically until, here's a non-irradiated case compared to the irradiated, you elevate the yield point. There's also the UTS relative to the unirradiated case. But when the material eventually does yield, it does so with a yield drop, and then in effect what we have then is softening. The material is much easier to deform after this point. And if we see a second drop, that's understandable, because what that means is that the first load drop corresponds with the initiation of one slip system, which can be according to the Schmidt factor, it just maybe the lowest of all possibilities. And the second load drop occurs because, in fact, when the material, when the gauge, when the tensile specimen is deforming and it's slipping, it loses its continuity with the load line. The points of connection between the load line of the load frame and the tensile specimen shift, and what that does is it induces constraints, and that induces a second slip system to occur that would bring the thing back into a more straight, I'll show you that in the next slide, into bring the load line back into place with the specimen length. Anyway, this is just an example of, here we have this dense array of defects, little clusters of atoms in platelets. And when we yield at this point, the dislocations sweep through the dislocation loops and actually sweep them out and make a layer, a couch, or a channel which is free of defects, which is actually softer. So again, here's another example where we have this yield drop and then a second yield drop, and eventually you get failure. So what I was talking about there was when you apply a load in a tensile specimen, the material will slip, and that will displace the connection points of the tensile specimen laterally. And if there's a load line in a particular direction, this will cause the material to elastically bend, and the applied elastic constraints will then initiate a second slip system if it's working perfectly, and then you get this double effect where slip on one direction moves one part of the specimen, the tensile specimen, in one direction relative to the load, relative to the other part of the specimen, or the load line if you like, and likewise if you have the other slip system operating which is symmetric to that, it goes in this way, and that way you get you bring the whole thing back into conformity with the load line during the testing. So this is a point of confusion often when people talk about slip, which is what you see here, where you get one part of the crystal gliding over the other. When people talk about slip causing bending, it's not slip that's causing bending, it's the constraints that cause the bending. And if you can even up the constraints in this way, then you have no bending, basically. So these softer channels, I just basically stated that the dislocations sweep out the dislocation loops and make them softer. But what's actually going on? Now, it's been subject to quite a bit of interest and research, the effect of channeling, what it is, how it's manifested in the strength of the material, and if it has any impact on the fracture of the material. Well, it does have an impact in the fracture, because what you actually have is you have localized easy deformation along certain layers or volumes within the material, and therefore high strains will build up. It's possible to deform in these softer regions more than anywhere else, and the fact that it's a lower volume, even though you've got a high strain in this narrower volume, the macroscopic strain may be quite low, but the microscopic strain in the channel is actually quite high. So this is actually a manifestation of some reduction in the ductility, and a lot of these ductility drops that we see associated with the high strength are primarily, primarily related to this feature in zirconium alloys. So here's some modeling results quite recently, in the last 5 years, showing what would happen is if you had a dislocation source here and you have a loop structure ahead of some dislocations, and these dislocations are traversing through the loop structure, and how these dislocations absorb the loops and climb on various planes. So here's an example of what I mean by that. You have a dislocation loop, which is like a platelet of atoms. A dislocation moves up to the platelet, and when it interacts, it will interact at some point here, and when it interacts, it sweeps up. So if you're because by climb, in effect, it will climb. So this dislocation here will climb, in effect, by this amount over the area of the loop, and then the dislocation can continue. This is, in this example, this is for perfect edge dislocations. A screw dislocation is just going to get hung up. Screw dislocation is, this doesn't work for screw dislocation, it only works for edge dislocations. So what does that look like on this kind of diagram? Well, we start off, we have a source of dislocations here. They start out traveling at time step 1, for instance, and they spread out because they're absorbing loops, and they climb. And the sign of the climb, the direction of the climb, is depending on the sign of the loop, of course. And if you had different signs of, well, you wouldn't have different signs of dislocations. You'd have the same sign if they're moving in the same direction. And then at some intermediate spot, this volume of material which is being swept out of, or which is interfering with the dislocations, increases as the dislocations climb further and further. And then at the end here, you have a region where you have this very broad distribution of dislocations. Now, once you got to this point, you've essentially got a subgrain boundary. So these dislocations are what is known as geometrically necessary dislocations, because this arrangement of dislocations in this way is the same as a subgrain boundary, and it actually creates a tilt in the crystal. Each individual dislocation does not tilt the crystal, but when they're in this arrangement and they've arrived at this location or this arrangement through climb, in effect, by sweeping up the dislocations, this is a means by which we can get some tilting of the specimen. At this point here, we have a much more diffuse situation, and it's just like having this subgrain boundary spread over a wider area. It's a little bit more of a diffuse subgrain boundary. So I should have clicked that. So this just describes what's going on. The channel progresses from time A to B to C, and the dislocations climb accordingly until we get to the end. And if this was butting up against a grain boundary, we'd have an array of dislocations which are very close to the boundary. And some people might mistake the tilt you would see of the crystal from these geometrically necessary dislocations as a stress, but it's not. It's actually this is a low energy configuration when the atoms of the dislocations are arranged like this. It's not the same as taking a simple elastic stress. Now, this process of sweeping was first proposed by a guy called Sharp back in Harwell back in 1975, I think it was. And it's now widely accepted, and nowadays with expensive computers, molecular dynamic simulations can quite readily show this effect of this climb effect, sweeping out areas or creating zones which are essentially free of dislocations when dislocations travel through an array of dislocation loops. Okay, so something worth mentioning, and this is generic both to steels and to zirconium alloys, is if you have an irradiated material and you have twins, now the twins may be there beforehand or they may be formed during irradiation. You may get a situation like this on the left-hand side where you have dislocation loops and what looks like a channel, but in fact it's not. What we have here is an array of dislocation loops and a twin. And this guy Onshi did the requisite tilting to show that this apparent channel was in fact a twin. And all that means is that when it's a twin, this crystal here in this band here is a different crystallographic orientation to the remainder of the matrix. So if you have a diffraction condition, as we show here, which is just suitable to show contrast, and I'm not going to go into a lecture on TEM, but it would require a lecture on TEM for you to get that, but just take my word for it. The diffraction conditions one sets up in an electron microscope, you set up particular direct diffraction conditions so that you can image defects like dislocation loops. And these dislocation loops might still be here, and in fact they probably are in this region, but the crystal has a different tilt at this point. And so we're not in the same diffraction conditions, and you don't see them. So there are many cases in the press and publications where people see this and say, aha, channel, but really they're wrong. It's not a channel. And unless they've done the requisite tilting, and unless they've said, and we tested to see that it's not a twin, then I wouldn't believe it, unless they've said, but we've shown that it's not a twin. In this case, Onshi showed that it was a twin, so we're all good. And there are too many cases where people have reported channeling and really not channeling. Okay, moving on. Fracture toughness. I've shown this a few times. We have this line broadening data as a function of fluence, showing, in this case, it's niobium pressure tube material, showing the increase in the line broadening, and it saturates, or more or less saturates, at a very low dose. Again, coincidentally with that, we have this decrease in the fracture toughness. In this case, it's dJ by dA, which is the crack opening energy increment. So dJ is the energy you input per unit increment in the crack extension. So this is somewhat similar to ductility that I showed in the other plots. We get this drop in the ductility, and then it saturates at the same time that the strength saturates, for the same reason, because we have damage in there. Now, another thing to be aware of, particularly important when it comes to zirconium alloys, is that the fracture toughness, although it'll vary from alloy to alloy, you have to be careful that you don't have some other effects coming into play and that you're aware of it. And one of the effects that has been documented when it comes to zirconium pressure tubes is the link with chlorine. And when you have chlorine present, here we have a plot showing increasing chlorine here, and we have fracture toughness, and we're comparing unirradiated with irradiated material. One sees that there is a relationship between the amount of chlorine and the decrease, the change in the fracture toughness. In this case, this would be for different samples from different locations, I guess, where for whatever reason we have a toughness value due to some variable. And I'm not sure what variable it would be, or variables they would be, but this just compares the unirradiated to the irradiated case. So when you have this decrement in fracture toughness with irradiation, but actually you also get the same decrement with high doses. So there doesn't seem to be much, if any, synergy between the role of chlorine and the delta in terms of fracture toughness radiation. But it's just as well to make note the fact that you get a significant drop in fracture toughness once the chlorine level is greater than 2 or 3. I think it's weight ppm in this particular case. So how the chlorine acts, there is some speculation that it has to do with some weakening of interfaces. It may also have an effect on the microstructure, and because chlorine, like many other impurities, has a role to play in grain refinement. And okay, so probably the most well-known and most problematic effect on fracture toughness is that of hydrogen. So as we increase the hydrogen content, if we pick a temperature here, if we look at the curve compact, no, not curve compact test, it's just impact test, Sharpie impact test, and we look at the impact energy, and we look at some low hydrogen content at a given temperature. When we increase the hydrogen content, this impact energy drops significantly. It's only when you're at a high enough temperature to be in the upper shelf, at here it occurs at 300 degrees C if it's 45 weight ppm, but it happens at much higher temperatures when the hydrogen content is higher. So it's only in the lower shelf region where we have some embrittlement from the hydrogen due to hydride formation, we see this effect of increase in the hydrogen. Part of that has to do with the fact of having hydrides basically being at a temperature where you're below TSSP. So if the temperature is below the temperature for precipitation, that then shows up as a drop in the fracture toughness. Similar kind of plot. It shows essentially the same thing. We have this essentially ductile to brittle temperature shift, and at high temperatures we have this, we're okay, we're in the upper shelf region. So the fracture toughness with respect to hydrogen in amounts that are mostly relevant to, say, fuel cladding, for instance, it's mostly relates to lower temperature operation or shifting to a lower temperature. And the type of hydrides is important. So we have radial hydrides, which I'll show you next. They're much more prone to having, if you like, a lower fracture toughness at a given temperature. So circumferential hydrides, which I'll show you now, are much more benign than the radial hydrides. So radial hydrides are really bad, and you want to avoid them. And what do I mean by that? Well, here's a cross-section through a tube. Circumferential hydrides all are platelets which lie within the plane of the tube, whereas the radial hydrides extend as platelets through the tube thickness. And it's very easy to see. You can imagine that if you have a crack and it follows a hydride, it's going to advance much quicker across the wall thickness in these cases than it would in these cases. But what is the combined effect of radiation damage in hydrogen? I showed that the combined effect of radiation with chlorine didn't seem to be very any synergy between the chlorine and the radiation damage. They're independent of one another, seemingly. But what about hydrogen? Well, when we look at fracture toughness as a function of hydrogen orientation, we see that I got ahead of myself here. This isn't about radiation, this is just hydride orientation. This is more about the same thing. When we have a lower temperature and a radial hydride. This just illustrates what I just showed you in that other diagram, which is basically at a certain point, there's a certain fraction of radial hydrides where the effect shows up, and it only shows up in the lower shelf at lower temperatures, but at higher temperatures, one can tolerate a large number of radial hydrides. So I omitted to talk about the effect of radiation on hydrogen, but suffice to say, radiation impacts fracture toughness, and hydrogen also impacts the fracture toughness. And just like with the chlorine, when you add them all together, they have combined effects which are harmful, of course. So hydriding is bad for fracture toughness, radiation is bad for fracture toughness, and chlorine is bad for fracture toughness. Okay, still dealing with hydrides, let's move on to hydride cracking, delayed hydride cracking. So what is delayed hydride cracking? Well, if you have a component and it's subject to a stress, or if you have an incipient crack, which is essentially still stressed, what you find is that hydrides will form at crack tip. And that's what is then the precursor for cracking in the hydride. So when you have a lot of hydrides forming at a crack tip, in this case it's a blunt notch, but it's still sufficiently high stress to nucleate the hydrides. When you have enough hydrides at the blunt notch, they will crack, as we see here. And what I should have done is shown that this would be subject to some tensile stress in this plane. So what's the essence of DHC? You start off with a crack, hydrogen in solution moves to the crack tip. There are various theories and models to describe this movement, but as a rule of thumb, hydrogen moves to sites of higher stress intensity. So higher stress or higher dilatational stress, higher pressure in the material, you'll get hydrides migrating to that region. So you get the hydride forming, especially along a crack tip, subject to a tensile stress as we've shown here. And then eventually the hydride gets to a certain size and it cracks. The reason it cracks at a certain size, that is still also subject to various theories and hypotheses. But what that means is that once you're in a regime, both of stress and temperature, where you can get this hydrogen accumulation at a crack tip, once we exceed a certain stress intensity, which is related to the stress, we can have this effect happening. We surpass a certain threshold, and we get into a stable crack growth region in terms of the crack velocity. So in this region, the stress intensity factor can be increasing quite a bit as we get to a sharper and sharper crack. And what happens is hydrogen will diffuse to the crack tip, essentially blunting it, but then it'll crack further. So you get this region of stable crack growth at a very steady rate until eventually, when the crack is extended far enough across the sample, you exceed K1C, which is the critical crack length, and unstable crack growth continues from that point on. The material breaks. So when it comes to radiation effects in DHC, there are two factors. And these are, because DHC is primarily a problem for the CANDU reactors, most of the work that's gone on looking at the effects of different conditions on DHC, including radiation, the primary thing that people look at is the beta phase. The beta phase is a short circuit path for diffusion, and when a tube is extruded, we have this continuous metastable beta phase. In the final heat treatment, it starts to decompose, and that actually makes it harder for material to diffuse along there. Because it's a beta BCC structure, hydrogen typically moves faster within this beta phase. It's very difficult to see what goes on during irradiation, but there are changes that happen between the unirradiated and the irradiated case. And again, just like with the dislocation loops, we monitor that with X-ray diffraction. So to finish off, just talking about some results on DHC, relating it to the microstructure for components removed from a reactor. Just a reminder what the fuel channel looks like. I showed you this in an earlier presentation, but in the CANDU reactor, we have a fuel channel with a pressure tube, kind of sinusoidal flux profile, and a temperature profile going from cold inlet to hot outlet. And if we take samples at different locations along the fuel channel relative to the flux and the temperature, what we see is that in terms of the beta phase, this dotted line represents the unirradiated state. And what happens is in the higher flux region, we actually get a reversal in the decomposition. So the material heals itself, or it becomes healed from the radiation damage. It mixes up the decomposed beta phase. But not so as we get to high enough temperature, because at the high enough temperature, the thermal effect, which further decomposes the beta phase, is stronger than any residual effect of the radiation damage, because the flux is so low at this point. The dislocation density affects the hardness, the mechanical properties, and that also affects DHC. And this just shows the integral breadth, the dislocation density profile as a function of actual location. The split here is because as the pressure tube expands, it actually gets hot on the bottom and cold on the top. I'm not going to go into that in any details right now, but basically all I want to say is that we get a peak in the damage density, which is around about 2 meters, and that peak corresponds to a trough in the niobium content, which is basically an indication of the continuity of the beta phase at the same location. So we get hardening, which basically reduces your fracture toughness, and or certainly increases your DHC behavior for sure as well. And at the same location, you get mixing of the beta phase, which basically makes it easier for hydrogen to migrate within the material. And we can correlate the DHC growth rates with either the line broadening of the radiation damage, showing the radiation damage, or we can correlate it with the niobium content. Unfortunately, they're both covariate, so we don't really know which one is dominating, or even if one of these factors is not important. It's very difficult to know what the mix of the effects are. In principle, both should have an effect, but they're both working in the same direction.